Hello everyone. My name is Kaiuli, and I am from Zhejiang University. In this work, we propose SegEarth-OV, the first open vocabulary segmentation method for remote sensing images, which provides a new solution to realize universal remote sensing image interpretation. Remote sensing images, like those from Google Earth, NASA Landsat, and Sentinel-2, have truly revolutionized how we observe and understand our planet. While acquiring raw remote sensing data is becoming increasingly accessible, obtaining large-scale, high-quality annotations remains a significant challenge. This is compounded by the fact that in many remote sensing applications, the need for pixel-level interpretation is often more frequent, which further intensifies the annotation bottleneck. One popular method to mitigate data scarcity is the OpenStreetMap project. It's a fantastic initiative aiming to create a freely usable, editable, and shareable map of the world. However, some studies have shown that the completeness of OpenStreetMap data can be significantly influenced by regional income levels. This creates geographical disparities and limits its universal applicability for comprehensive global analysis. In recent years, the rapid development of vision language model has made open vocabulary semantic segmentation, or OVSS, a viable solution in natural images. The typical training-free OVSS framework leverages a pre-trained CLIP model. During CLIP's training phase, as shown on the left, paired image embeddings and text embeddings are aligned in a shared space. The image embedding is usually represented by a global class token. And for OVSS inference, as shown on the right, our goal is to produce dense, pixel-level predictions. To achieve this, we utilize the local image features, or patch tokens, and compute their similarity with text features derived from category. This forms the basis of most training-free OVSS pipelines. So, our first step was to apply state-of-the-art OVSS methods developed for natural images, such as mask clip and clear clip, directly to remote sensing imagery. As you can see from these qualitative results, their performance is often suboptimal. The main issues are inaccurate localization and ill-fitting boundaries in the predicted segmentation masks. We believe a primary reason for this is the inherently low resolution of the feature maps used by these OVSS methods. In standard clip-based OVSS, the feature maps are downsampled to just 1/16 of the original image resolution. This significant loss of spatial detail is particularly detrimental for the fine-grained information present in remote sensing images. This challenge motivated us to explore methods for upsampling these low-resolution features. Our inspiration came from FeetUp, a work presented at iClear 2024. FeetUp extracts low-resolution features using a frozen backbone. It then employs a learnable upsampler and a learnable downsampler to reconstruct these initial low-resolution features, guided by the reconstruction loss shown here. After training, the learned upsampler can be used to generate higher-resolution features. However, for our specific task of training free OVSS on remote sensing images, FeetUp has two key limitations. First, it's primarily designed for natural images, and second, it's applied within a training-based setting. Therefore, we adapted and improved FeetUp, leading to our module, SimFeetUp. The first improvement addresses image content retention. While FeetUp constrains the reconstructed low-resolution features, it doesn't explicitly ensure that the intermediate high-resolution features, which are our actual goal, remain consistent with the original image content. This visualization on the left illustrates the problem. The red circle highlights a small building. When we use the low-resolution features directly from CLIP for inference, the building is detected. However, after upsampling with the original FeetUp, this building disappears. To address this, we introduce a lightweight content retention network, or CRN, which takes the high-resolution features as input and reconstructs the original image. This CRN, consisting of just two convolutional layers, is only used during SimFeetUp training and discarded at inference. As you can see, with the CRN, the building is well preserved after upsampling. The next question is, which features should we upsample? Let's briefly revisit CLIP's VIT-based image encoder. It's a series of transformer blocks. Let X be the input to the last block, comprising a global class token and local patch tokens. After the attention and FFN layers, we get an output C, which is then projected to O. In the original feetup, the patch token part of O is upsampled. However, for OVSS, many studies have shown that vanilla self-attention can introduce noise. Thus, it's common to replace it with self-attention variants during inference. This creates a mismatch if SimFeetup is trained to upsample O derived from the original attention. Therefore, in our method, we choose to upsample features from an earlier stage, specifically, the patch token input X to the last transformer block. To manage computational cost due to X's higher dimension, we retain the original projection layer. So, we effectively upsample O', which is the projection layer applied to the patch token part of X. Let's delve into the upsampler's internal structure. Feetup uses stacked parameterized joint bilateral upsampling, or JBU, operators. Essentially, the upsampled high-resolution feature is a weighted sum of neighboring low-resolution features. The JBU generates these weights based on two factors: spatial distance, k-spatial, and feature similarity, k-range, between the center element and its neighbors, computed within a window of radius r. Remote sensing images exhibit greater scale variations for the same object class compared to natural images. Think of a single tree versus an entire forest. To capture this, we expanded the upsampling kernel from feetup 7 to 11, providing a wider receptive field. While larger kernels might risk introducing irrelevant context, the k-spatial term naturally downweights distant elements, making this effective. Finally, we simplified the upsampling network. The original feetup stacks 4 distinct JBU modules for 16 times upsampling. We streamlined this to JBU1, using only a single parameterized JBU module. If 16 times upsampling is needed, this single JBU is applied repeatedly. This simplification makes the behavior of each upsampling step is more consistent. And it provides the flexibility to upsample by arbitrary multiples. Recall that during clip training, it's the global class token that's optimized. But in OVSS inference, we use local patch tokens. This creates a training inference gap. We conducted an experiment shown on the left. For the RGB image, clip's class token correctly classifies it as building because buildings dominate the scene. However, when we compute the similarity between this class token and all patch tokens, we find that high similarity regions include not just buildings but also some roads and pavements. This indicates that global image properties are leaking into, or biasing, the local patch tokens. This global bias is problematic for dense prediction tasks. So, we propose a very direct and simple solution: subtract this global bias from the patch tokens, as formulated on the right, where O0 is the class token. We conducted extensive experiments on 17 remote sensing datasets, covering semantic segmentation, building extraction, road extraction, and flood detection. This main table here shows a significant average improvement of 5.8 MIU points over state-of-the-art natural image OVSS methods on 8 diverse semantic segmentation datasets. The task-specific tables further confirm these gains, especially for building extraction, where fine details are crucial, and for flood detection. We also tested different input image resolutions, finding that larger inputs generally benefit road extraction and building extraction on certain datasets. We also performed comprehensive ablation studies to validate our design choices. First, as shown in the ablation table on the left, every component we introduced is effective. Second, our plug-and-play experiments, detailed in the middle table, demonstrate the generality of our proposed methods. Third, as shown in the right table, our SimFeetup module also benefits general vision tasks. Finally, we evaluated existing remote sensing specific clip models in the OVSS setting. While models like GeoRS Clip show some utility, their impact isn't overwhelmingly significant, suggesting that merely pre-training clip on RS data doesn't fully solve OVSS challenges. This underscores the importance of methods like ours that address fundamental feature representation issues. In summary, SegEarth-OV is the first training-free open vocabulary segmentation method specifically tailored for the unique challenges of remote sensing images. We've demonstrated that by systematically addressing feature resolution with our SIM-feedup module and mitigating global bias in patch tokens, we can achieve significant performance gains, offering a new and promising pathway towards universal remote sensing image interpretation. Thank you very much for your attention. We encourage you to follow our future research in this exciting area. If you have any questions, do not hesitate to contact us.